Okay. Here we're talking about a route choice problem. We have our origin A and destination D. So I'm going to call this origin point A is my origin. And I have travelers going from origin to node D, which is a destination. And these are all sort of one-way link. That's what it's denoted here. I should probably say it here. D is my destination. And because these are all one-way link, you can either take ABD path or you could take the ACD path. Okay, so these are the two paths, route 1 and route 2 you have. And then each of these links right here have, all four of these links have what we call link performance function, and those are all linear in nature. Okay, those are all sort of linear in nature. So on link AB, link time flow function, I have on AB, it's 5 times QAB. So whatever is the number of vehicles passing through A to B, I get my travel time will be 5 times QAB. For BD, it's 25 plus QBD. For AC, it's 20 plus 2 QAC. And for CD, it's 5 times QCD. Okay, so those are sort of my link performance function for all four of those links. Now here, before I can go ahead and solve the problem that it's asking me to solve, it's asking me how should I divide the flow between two routes using user equilibrium principle and the system optimal principle. And then I'm also trying to do, what I'm also trying to do is I'm trying to determine the price of anarchy. So here, first thing I need to do is think about, so if I need to figure out how many people are going to choose this route, route ABD, how many people are going to choose route ABD, and then how many people are going to choose route ACD. Okay? So that's what I'm trying to figure out, route ABD and route ACD. Now, for route ABD, I can apply the conservation of flow principle, first of all, because again, I need to figure out, if these two I need to figure out, but I have all these QAB and QBD, but I can see some relationship between AB and BD, right? I can see that because of this, because of conservation of flow, I could say QAB should be equal to QBD, because whoever comes in at B has to go towards this, should be equal to QBD, and I could call it equal to QABD route. Okay, so I can call it QABD. Yeah, so these are sort of my subscript. I just think of these. And then same thing, I could say QAC equal to QCD equal to QACD. So people who are going to take the route ABD are all going to be on this path, and people who are going to take route ACD are all going to be on this path. So I really typically have, I really only have two routes that I'm taking, and I need to figure out what's QABD and what's QACD. That's all I need to figure out. Let's call QABD Q1. That's just easier to write down, and QACD to be Q2. So this is sort of my route 1 and route 2. So let's call them route 1 and route 2. I need to figure out ABT is my route 1 and ACD is my route 2. I need to divide the traffic flow in those two routes according to the user equilibrium principle and the system optimal principle. Okay, so let's just do user equilibrium principle. There is a total of 6 units of flow. So it could be 6,000 vehicles per hour. It could be 600,000 vehicles per hour, whatever it is. However I'm measuring it, it's just total is 6 units. And I need to figure out So first of all, I need to write down. So I have these link performance function, but I need to then route, then I need to write down my route performance functions based on these link. Okay. So I can write down my route performance function. If you take route ABD, which is route 1, my route performance function would be how much travel time would it take to go from A to B and then B to D. I can apply these equations that are given to me. So for my route performance function will be 5 times. So for my route 1, route for travel time on route 1, travel time will be equal to 5 times QAB plus 25 plus QBD. That makes sense? But all I'm doing is I'm taking these equations and I'm adding up the travel time on the first link and on the second link. Okay, but now remember, I already called QAB equal to QBD equal to Q1. So all I can say is it's basically 5 times Q1 plus 25 plus Q1. That means it's equal to 25 plus 6 Q1. Okay. And then for route 2, travel time. Similarly, I can figure out it's 20 plus so for route 2, I can figure it out. So I'm going to rewrite those equations now that you know how to write them. For route 1, so travel time on route 1 will be equal to 25 plus 6 Q1. Okay. And then same thing, I can do the same thing for route 2. Okay. It'll be 20 plus 7 Q2. To do this, I just added the route travel time, route AC, and then route CD. So these are basically equations that describe the travel time that's going to take on each link, and I just add up those times on those links. So I need to first find out Q1 and Q2 using the user equilibrium principle. So now think about, if you are the first traveler going on these routes, which route would you take? When the flow on both of these routes is 0, when Q1 is 0 and Q2 is 0, the route 1 will take 25 minutes, route 2 will take 20 minutes. So if you're the first traveler, you'll obviously take route 2, right? Because it takes less amount of time. So that's the sort of the principle that we use, is that everybody tries to minimize their travel time. So you keep taking this route. Now, for how long would you keep taking this route? People will keep taking this route until the travel time on this route becomes at least 25. Because once the travel time on route 2 becomes 25, then people say, hey, now I should probably take route 1 because it's only take 25 minutes, even because nobody's still using route 1. It's going to take 25. So that would be the threshold where both routes start getting used. So anytime I'm trying to solve a user equilibrium equation, this is the most important thing, is that you need to figure out the threshold at which all routes start getting used. In this case, there are only 2 routes. So when would the second route start getting used? So this is the first step, is to find the threshold. So I'm going to write this down here. So your first step is find the threshold for route 1 to be used. And why route 1 is at risk? Because initially everybody will take route 2. Okay. Route 1 will start getting used when 20 plus 7Q2, when there are enough people using Route 2 that the travel time on Route 2 has become at least 25. Why 25? Because that's the travel time it takes on Route 1 when Q1 is 0, when Route 1 is empty. So I can figure out the threshold for Q2 threshold is 5/7, which is you could figure it out about 0.71 units. So this is an important lesson here, is that if instead of given a flow of 6 units, if you're given a flow of 0.5 units, according to user equilibrium, your answer will be all of the traffic will go to Route 2, nobody will go to Route 1. So anything less than 0.71 units of total flow, all of the traffic will go to Route 2. Nobody will use Route 1 because Route 1 takes 25 minutes. And at the flow rate below this threshold, you're better off just choosing Route 2 and nobody going to Route 1. Okay, so that's one way sort of capacity is sometimes not used when people are using user equilibrium, but everybody would use user equilibrium because they're trying to minimize their own travel time. Now, in this case, we don't have a problem because our total flow rate is 6 units. That means both routes will in fact be used. Okay, so both routes will be used. So it is less than 6 units of total demand given. Hence, both routes are used. Now, important thing for you to note is that if you go back, I underlined all used route will be travel time are equal on all used route. Okay, so it's very important for you to first figure out that you figure out the number of routes being used. Okay, so that's pretty critical here. And because our total flow is higher, the given demand is higher than the threshold, that means both routes will be used. And now we can apply the user equilibrium principle more easily. And to do that, it's fairly simple. You know, all we need to do is come up with 2 equations for Q1 and Q2. First equation will be based on conservation of flow, which is Q1 plus Q2 equal to 6 units. Q1 plus Q2 equal to 6. So that's your one equation. And the other equation will be coming from the user equilibrium principle, which says the travel time on 2 routes has to be equal. It'll be 25 plus 6 Q1 plus or equal to, should be equal to 20 plus 7 Q2. And again, now you have 2 unknowns and 2 equations, and I'll let you kind of solve that and figure out the values for Q1 and Q2. And those will be sort of your values of how the flow will be divided between the 2 routes. Okay. Now, according to user equilibrium principle, so these are the 2 equations. These are the 2 equations for user equilibrium principle. Now, for system optimal, that's not how it works. For system optimal, we try to minimize the aggregate system travel time. Okay, aggregate system travel time. So how do we do that? To get the aggregate system travel time, what we need to do is figure out how many vehicles are using Route 1 and how many vehicles are using Route 2. And remember, travel time on Route 1, this 25 plus 6Q1 equation that I'm dealing with here, 25 plus 6Q1 and 20 plus 7Q2 equation, that's the travel time that one vehicle is taking on this route. So anybody who's going in this route, it's going to take this much travel time. depending upon how many people are using that route. And then, so if, so let's say if there's 1 unit of flow on route 1, each vehicle that is going on that route, it's going to take 25 plus 6 times 1. That's 31 units of travel time for that one vehicle. If I want to get the aggregate travel time for those vehicles, I again multiply that by Q1. So for system optimal, okay, so for system optimal, so I'm going to, so for system optimal, what I'm going to do is, figure out aggregate travel time on each route. And how do I do that? For route 1, it will be Q1 multiplied by the travel time that each vehicle is taking. It will be Q1 times 25 plus 6Q1. Okay. Right. And on route 2, it will be what will be the route 2 aggregate travel time? It will be Q2 times 20 plus 7 times Q2. Okay. So now I've figured out what I've done is, I've figured out the aggregate travel time on both routes individually. And if I add that, I can get the total system travel time. I can get the total system travel time. Okay. Good news is that my conservation of flow principle still applies. I cannot use this equation where travel time on both routes are equal for my system optimal assignment, but my conservation of flow equation is still valid. So I can still say that Q1 plus Q2 equal to still 6 units. So my Q1 plus Q2 will still add up to be 6 units, and I will be able to get that. That's pretty good. And I can then figure out what would that look like. Okay. Now, to get the system optimal travel time, I need to minimize what's represented, this aggregate system travel time that's represented by this equation right here. So how do I do that? I do that by representing all of this in terms of one variable, and then remember to get a minima of a function, I differentiate that equation and set the derivative equal to 0. So what I'll do is I'll just do Q1 equal to 6 minus Q2. I plug that into this equation. And once I plug that into that equation, I'll get those values. Okay. So and then I try to minimize that value. Hi everyone. So I'm back, and I calculated the user equilibrium values of Q1 and Q2, and I calculated system optimal values of Q1 and Q2 as well. So this is what they look like. So for user equilibrium, Q1 is 2.85. Q2 is so the flow on route 1 is 2.85, Q2 is 3.15. And then when I applied the system optimal, which was when I applied the system optimal principle, where I wrote down the expression for, so remember I wrote down the expression for total system travel time, which was individual person's travel time times how much time it was taking and how many people were using that. And the expression there was 25 times Q1 plus 6 times Q1 squared plus 20 times Q2 plus 7 times Q2 squared So that was my expression for the total system travel time. And once I did that expression, remember this was the travel time on route 1 aggregate for all users. This part was the travel time on route 2 aggregate for all users. Remember, we call this route 1, we call this the route 2. So this is route 1, this is route 2. And then this was our total system travel time expression. And once we minimize it using the expression Q1, we minimize it using the expression that Q1 plus Q2 is still 6. So Q1 will be equal to 6 minus Q2. And then I use that expression. I substitute Q1 with 6 minus Q2. And then I differentiate it with respect to Q2. And I solve for Q1 and Q2. So my system optimal values, system optimal SO values for flows will be Q1 equal to 3.04. I should be able to solve that. And Q2 equal to 2.96. Okay, so I got those. That's pretty good. Okay, so that should be in good shape. Now, because these values are different for user equilibrium and system optimal, they lead to total system travel time being different depending upon what the equilibrium flow you use. So if you use the user equilibrium flow in this equation, if you use this user equilibrium flow in this equation, your total system travel time will come out to be about 252 units. So if you use using UE values of flow rates, you get TSTT, the total system travel time, the TSTT value to be about 252.44 units. But if you use these values that are system optimal, you get using SO value of flow rates, you get the total system travel time of only 252 units. Okay, so if you use these values, you're going to get a total system travel time of 252 units. So as you can see, the total system travel time still leads to, if you do the system optimal assignment, that leads to a lower amount of travel time. Okay, so that's what we are trying to say here. And if I want to just estimate the price of anarchy, it's pretty simple. All I need to do is figure out what is the ratio between 252.44 divided by 252. And whatever that ratio comes out to be is my price of anarchy. I'll let you do the calculations. And I would also love for you to verify these values. You should be able to obtain on your own this Q1 and Q2 value using the user equilibrium principle, 2 equations, 2 unknown, and then minimizing this total system travel time equation based on just one of those variables, and then solving and setting the differential equal to 0 and be able to get Q1 and Q2. If you have any questions, feel free to reach out. So last but not the least, I want to just quickly mention some trends in the planning process. Let's say if you live in Southern California, for example, we are now giving explicit consideration to freight and the heavy vehicles in our travel demand modeling, which we did not do it initially. We are integrating ITS, for example, more traveler information is available to users through intelligent transportation systems, ITS. So we're accounting for that. We're accounting for how many crashes are expected. We talked about that in our safety lessons a little bit. So we're accounting for the highway safety manual in our planning process. And last but not the least, the federal government, because they fund a lot of the transportation infrastructure, they want the planning process to identify alternatives based on a continuous comprehensive and a cooperative process. So public engagement is becoming pretty critical in the process. A lot of these metropolitan planning organizations are doing that now, which did not always happen, but I think it's probably valuable to have. So those are some of the trends in the planning process. Again, you learn those in CE 523 class, which is the travel demand modeling class, CE 529 class, which is the modeling and simulation class, and then CE 528, which is the transportation economics and analysis class. So I'll recommend those classes if you're interested in those topics. With that, I'm going to just conclude this lecture. If you have any questions, feel free to reach out. Thank you so much.